So here's something worth thinking about as you settle in tonight. Right now, wherever you are, you're surrounded by sound. Maybe it's the hum of an air conditioner, or traffic somewhere in the distance, or just the soft rhythm of your own breathing. Sound is so constant, so everywhere in our lives, that we almost forget it's there. It's like wallpaper for our existence. But here's the thing. Step outside this planet, go just a little ways up, maybe 100 kilometers or so, and all of that vanishes, every bit of it. The universe out there is, for all practical purposes, silent, profoundly, almost incomprehensibly silent, and not just quiet the way a library is quiet or the way a snowy field at midnight is quiet. Those places still have sound. They're just low on it. Space is different. Space doesn't do sound at all. Not because it's being polite, not because there's nothing happening out there. There's plenty happening. Stars are exploding. Galaxies are colliding. Black holes are swallowing entire solar systems. The violence out there is on a scale that makes anything on Earth look like a hiccup. And yet, silence. Total, perfect, unbroken silence. Why? What is it about the emptiness between the stars that refuses to carry a sound wave? That's what we're going to talk about tonight, slowly, gently, one piece at a time. And I promise you, it's more interesting than you might think. Let's start with something simple. What is sound, actually? Not the philosophical version, not if a tree falls in the forest. The real, physical, engineering version. Sound is a pressure wave. That's it. That's the whole thing. When you clap your hands together, you're not launching some mysterious energy into the air. What you're doing is shoving the air molecules right next to your hands into the air molecules next to them, which bump into the ones next to them, and so on, outward in every direction, like a ripple spreading across a pond. Each little cluster of air molecules gets compressed, pushed together, and then springs back apart, and that compression travels outward. Your eardrum, this incredibly thin membrane deep inside your ear, picks up that pressure wave when it arrives, vibrates in response, and your brain interprets that vibration as a clap. That's sound. It's mechanical. It's physical. It requires stuff, molecules, atoms, particles of some kind, to push against each other and pass the wave along. And this is the key to everything we're going to talk about tonight. Sound needs a medium. It needs material to travel through. Air works great. Water works even better, actually. Sound travels about 4 times faster in water than in air, roughly 1,480 meters per second, compared to about 343 meters per second in air at room temperature. Steel is even faster, around 5,960 meters per second. The denser and stiffer the material, the faster sound can move through it, because the molecules are packed tighter and they transmit that push more efficiently. Think of it like a line of people standing shoulder to shoulder. If you push the person at one end, the push travels down the line almost instantly because everyone's already touching. Now imagine those same people spread out across a football field with big gaps between them. You push the first person, they stumble forward, eventually reach the next person, push them. It's slow, sloppy, and if the gaps are big enough, the push never makes it to the other end at all. That's space. Space is the football field where the gaps are so enormous that there's effectively nobody left to push. Now, I want to be careful here, because when people say space is a vacuum, that's mostly true, but not perfectly true, and the difference actually matters. A perfect vacuum would mean 0 particles, absolutely nothing, not a single atom floating around. Space isn't quite that empty. In the interstellar medium, that's the stuff between stars within a galaxy, you typically find about 1 atom per cubic centimeter. 1. In the air you're breathing right now, there are about 2.5 times 10 to the 19th molecules per cubic centimeter. That's 25 followed by 18 zeros. So the difference between the air in your room and the void between stars is not just big, it's almost meaningless to try to compare. It's like comparing a single grain of sand to all the beaches on Earth. The density of particles in interstellar space is so absurdly low that for any practical purpose involving sound, it might as well be zero. But here's what's interesting, and this is something that tripped up some very smart people for a very long time. The idea that sound can't travel through a vacuum isn't obvious. It's actually kind of counterintuitive if you don't already know the physics. For most of human history, people had no reason to think about this at all. Sound was just something that happened. You spoke, people heard you. Thunder crashed, everyone flinched. It was as natural and unremarkable as gravity. The ancient Greeks, who thought about everything, had some ideas about sound, but they were mostly wrong in the specifics even when they were right in spirit. Pythagoras, around 500 BCE, was fascinated by the relationship between sound and mathematics. He figured out that musical harmony was related to simple numerical ratios, which is genuinely brilliant and completely true. If you take a vibrating string and cut its length in half, the pitch goes up by exactly 1 octave. Cut it to 2/3, you get a perfect fifth. He discovered this by listening to blacksmiths' hammers, or so the story goes, noticing that hammers of different weights produced different tones. The exact story is probably embellished, but the core insight was real and profound. Sound follows mathematical rules. But Pythagoras and his followers didn't really understand what sound was made of physically. They knew it had something to do with vibration, but the idea that it was a wave of pressure moving through air, that took a long time to develop. Aristotle, about a century and a half later, got closer. He proposed that sound was carried by the air, that it involved the air being set in motion. He even suggested that sound couldn't exist without something to carry it, which turns out to be exactly right. But Aristotle said a lot of things, and not all of them were correct. And in the centuries that followed, his ideas got tangled up with a lot of other philosophical baggage that made it hard to separate the good insights from the bad ones. The real breakthrough in understanding sound, the moment when people started to actually test whether sound needed a medium, didn't come until the 1600s, and it came from one of the most beautifully simple experiments in the history of science. In 1654, a German scientist and politician named Otto von Guericke, and this guy is a character worth knowing about, demonstrated something extraordinary in front of the imperial diet in Regensburg. Von Guericke had invented an air pump, one of the first effective vacuum pumps in history, and he used it to evacuate the air from between 2 large copper hemispheres, each about 50 centimeters in diameter. Once the air was pumped out, the hemispheres were held together by nothing but the pressure of the atmosphere pushing on them from the outside. And here's the showmanship. He hitched teams of horses to each hemisphere and had them pull in opposite directions. The horses couldn't pull them apart. The atmospheric pressure was just too strong. This was the famous Magdeburg Hemispheres demonstration, named after the city where von Guericke was mayor. And it was a sensation. It proved that air had real, measurable pressure, and that a vacuum, or something close to it, could be created artificially. Now, von Guericke himself did some experiments with sound and his vacuum pump. He reportedly placed a bell inside a glass vessel and pumped out the air, and noticed that the bell became quieter as the air was removed. But the results were a bit ambiguous. His pump couldn't create a perfect vacuum, and sound could still travel through the glass walls of the container and through whatever mounting held the bell in place. The experiment was suggestive, but not conclusive. The person who really nailed it was Robert Boyle, the Anglo-Irish natural philosopher, working in Oxford in the late 1650s and early 1660s. Boyle had access to a much better vacuum pump built by his brilliant assistant Robert Hooke. Yes, the same Robert Hooke who would go on to discover Hooke's law of elasticity and get into that legendary feud with Isaac Newton. Hooke was one of those people who could build anything, a mechanical genius, and the pump he constructed for Boyle was the best in the world at the time. Boyle placed a watch with a ticking mechanism inside a glass receiver and pumped out the air. As the air was removed, the ticking grew fainter and fainter until it was nearly inaudible. When he let the air back in, the ticking returned. He did the same thing with the bell. Same result. The conclusion was clear. Sound required air to travel. Remove the air, and the sound disappears. Now, Boyle was careful. He was a meticulous experimenter, one of the founders of modern experimental science, and he noted that the results weren't absolutely perfect. Some faint sound could still be detected even at the lowest pressures his pump could achieve, probably because of vibrations traveling through the mounting apparatus and the glass itself. But the trend was unmistakable. Less air meant less sound, and the implication was powerful. In a true vacuum, there would be no sound at all. Think about what that meant in the 1660s. People were just beginning to understand that the Earth was surrounded by an atmosphere, a finite shell of air, and that beyond it lay what? Nobody knew for sure. But if sound needed air, and space had no air, then space was silent. The stars, the moon, the planets, all of it wrapped in silence. That must have been a strange and somewhat unsettling thought for people who had grown up in a world where sound was everywhere. And here's where it connects to something bigger, something that was going to become one of the most important questions in physics for the next 300 years. If sound needs a medium, what about light? Light clearly travels through space. We can see the sun, we can see the stars. So either light doesn't need a medium, which would make it fundamentally different from sound, or there's some invisible medium filling all of space that light travels through, something we just can't detect directly. This question, does light need a medium, was going to haunt physics for centuries and lead to some of the most profound discoveries in human history. But we'll get to that. For now, just hold on to the idea. Let it sit in the back of your mind, because it's going to matter a lot later. What Boyle and his contemporaries had established was this foundational principle. Sound is mechanical. Sound needs stuff to travel through, and where there is no stuff, there is no sound. Simple, elegant. And it immediately raises a question that's surprisingly deep when you really sit with it. How empty is empty? Because if sound needs particles to propagate, then the question of whether sound can travel in space is really a question about how many particles are out there and whether there are enough of them packed closely enough together to pass a pressure wave from one to the next. And the answer, as we started to touch on, is that space is empty in a way that's genuinely hard for the human mind to grasp. We use the word empty casually, an empty room, an empty glass. But those things aren't empty at all. An empty room is absolutely stuffed with air, trillions upon trillions of molecules bouncing around at hundreds of meters per second, colliding with each other billions of times per second. Even the best laboratory vacuum we can create on Earth, using the most advanced pumps available, still contains thousands of molecules per cubic centimeter. Compared to interstellar space, our best vacuum is a thick soup. But here's something that might surprise you. The emptiness of space isn't uniform. It varies enormously depending on where you are. Near the surface of the Earth, obviously, you've got a full atmosphere. All that lovely dense air. Go up to the altitude where the International Space Station orbits, about 400 kilometers, and you're in what's called the thermosphere. The air density there is maybe a billionth of what it is at sea level. Still not a hard vacuum by space standards, though. There are enough stray molecules up there to actually create a tiny but measurable drag on the station, which is why it needs periodic boosts to maintain its orbit. Go further out, past the moon, into interplanetary space, the space between the planets within our solar system, and you find the solar wind, a stream of charged particles flowing outward from the sun. The density there is roughly 5 to 10 particles per cubic centimeter near Earth's orbit. That's incredibly thin, but it's still 1,000 times denser than the interstellar medium between stars. And in the vast voids between galaxies, the intergalactic medium drops to something like 1 atom per cubic meter. Per meter. Not per centimeter. Per meter. That's 1,000,000 times emptier than the space between stars, which was already almost inconceivably empty. So when we talk about sound not traveling in space, what we're really saying is that the mean free path, that's the average distance a particle travels before bumping into another particle, is so enormous that no coherent pressure wave can form. In the air around you right now, the mean free path is about 68 nanometers. That's tiny. Molecules are constantly slamming into each other, which is exactly why sound propagates so well. In interstellar space, the mean free path can be on the order of billions of kilometers. A particle could travel from the sun to well past Pluto before it encountered another particle to bump into. You can't build a pressure wave out of that. It's like trying to start a Mexican wave in a stadium where each person is sitting in a different country. And yet, even knowing all of this, even understanding the physics perfectly well, there's something about the silence of space that remains deeply strange to us. We are creatures of sound. Our brains are wired to expect it, to interpret it, to be alarmed by its absence. Total silence is actually uncomfortable for most people. That's why sensory deprivation chambers are so disorienting. We evolved on a planet drenched in sound, where silence often meant danger, and our nervous systems never quite got over that. So the idea of a universe that is overwhelmingly, crushingly silent, where the most violent events imaginable unfold without a whisper, that cuts against something deep in our intuition. And it raises a question that scientists have actually spent a surprising amount of time thinking about, which is whether there are any circumstances, anywhere in space, where something like sound could actually propagate. Because remember, we said space isn't perfectly empty. There are particles out there. Not many, but some. And in certain places, inside nebulae, in the hot gas surrounding galaxy clusters, the density is actually high enough that pressure waves can, in theory, form. The question is what those waves would look like, and whether you could ever really call them sound. And the answer, it turns out, is yes, but with some pretty wild caveats that tell us a lot about what sound actually is when you strip it down to its most fundamental definition. So let's think about this. We've got these galaxy clusters, right? These are the largest gravitationally bound structures in the universe. We're talking about hundreds or even thousands of galaxies, all held together by gravity. And between those galaxies, filling the vast spaces within the cluster, there's this incredibly hot gas. We're talking tens of millions of degrees. It's so hot that the gas is fully ionized. The electrons have been stripped away from their atoms, so what you've got is a plasma. And here's the thing. Even though this gas is extraordinarily thin by any earthly standard, by the standards of space, it's practically a crowd. The density in the core of a galaxy cluster might be something like 1,000 particles per cubic meter. Now compare that to the air you're breathing, which has something like 25 trillion molecules per cubic meter, and you realize that 1,000 particles per cubic meter is still almost nothing. But compared to the 1 particle per cubic meter you'd find in the deep void between galaxy clusters, it's 1,000 times denser. And that turns out to be enough. In 2003, a team of astronomers led by Andrew Fabian at the University of Cambridge made a discovery that genuinely stunned people. They were studying the Perseus galaxy cluster, which is about 250 million light-years from Earth, using the Chandra X-ray Observatory, a space telescope that sees in X-rays, which is exactly what you need to observe gas that hot. And what they found, when they looked closely at the X-ray images of the gas filling the cluster, were ripples. Concentric ripples spreading outward from the center of the cluster, where a supermassive black hole sits at the heart of a galaxy called NGC 1275. These ripples were pressure waves. They were, by any reasonable physical definition, sound waves. Sound waves propagating through the hot intracluster medium, driven by the periodic eruptions of that central black hole as it swallowed material and belched out jets of energy. Now, here's where it gets genuinely wonderful, and I want you to just sit with this for a moment. They calculated the frequency of these sound waves. The wavelength of the ripples was enormous, about 36,000 light-years from peak to peak. And when you work out what frequency that corresponds to, given the speed of sound in that hot plasma, you get a note, an actual musical note. And that note is a B-flat. But it's a B-flat that is 57 octaves below middle C. To put that in perspective, the lowest note a human ear can detect is about 20 hertz. This note in the Perseus cluster has a frequency of about 1 cycle every 10 million years. You'd have to wait 10 million years for a single oscillation of this wave to complete. It is, as far as anyone knows, the lowest note in the universe. And I love this story because it does something really important for our understanding. It doesn't contradict anything we said earlier about space being silent. You still couldn't hear anything if you were floating out there. These pressure waves have wavelengths thousands of light-years long. Your eardrum is, what, about a centimeter across? You'd be like an ant trying to detect an ocean swell. The wave would wash over you and you'd experience absolutely nothing. And the gas is still so thin that in any practical human sense, it's a vacuum. But in the strict physics sense, pressure waves are propagating. Sound exists there. It's just sound on a scale so vast and so slow that it belongs to a completely different world than the one our senses evolved to navigate. And this is a good moment to talk about something that I think makes the silence of space even more interesting, which is all the ways that the universe is incredibly loud, just not in sound. Because the universe is absolutely screaming with information. It's just using channels that our ears can't pick up. Think about light. Light doesn't need a medium. That was one of the great revelations of physics, and it took centuries of confusion and argument to nail down. Remember earlier when we mentioned that question? If sound needs a medium, does light need one too? Well, for a very long time, the answer that most physicists gave was yes. They called the medium the luminiferous ether. And the story of how that idea rose and fell is one of the great detective stories in all of science. The idea goes back a long way. When Christian Huygens proposed his wave theory of light in 1678, he naturally assumed that if light was a wave, it had to be waving through something. That's just how waves worked, as far as anyone knew. Water waves need water. Sound waves need air or some other material. So light waves must need what? Some invisible substance that fills all of space, that permeates everything, that's rigid enough to transmit waves at enormous speed, but somehow offers no resistance to the motion of planets. They called it the ether, and for about 200 years, most physicists simply accepted that it had to exist, even though nobody could detect it, touch it, or measure it directly. And here's what's fascinating. The ether wasn't a lazy assumption. Really brilliant people spent enormous effort trying to work out its properties. The speed of light is fast, about 300,000 kilometers per second, and for a wave to travel that fast through a medium, the medium has to be incredibly stiff. Think about how sound travels faster in steel than in air. That's because steel is much stiffer, much harder to compress. So the ether would have to be far stiffer than any known material. And yet planets glide through it without slowing down, which means it can't exert any friction. Those two requirements, extraordinary rigidity and zero friction, are basically contradictory for any normal substance. But physicists just sort of shrugged and said, well, the ether must be a very unusual substance. The person who really set out to settle the question was Albert Michelson, an American physicist who was obsessed with precision measurement. Michelson was born in 1852 in what is now Poland, but his family emigrated to the United States when he was a child, and he grew up in mining towns in Nevada and California during the gold rush era. He went to the Naval Academy, became fascinated with optics, and by his late 20s, he had already made the most precise measurement of the speed of light that anyone had ever achieved. He was a meticulous, driven, somewhat difficult man, the kind of person who would redesign an entire apparatus because the results were off by a fraction of a percent. Michelson's idea was elegant. If the Earth is moving through the ether, and it must be since the Earth orbits the Sun at about 30 kilometers per second, then the speed of light should be slightly different depending on which direction you measure it. If you shine a beam of light in the same direction the Earth is moving, it should appear to travel a tiny bit slower relative to you because you're chasing it through the ether. And if you shine it perpendicular to the Earth's motion, the speed should be different again. The difference would be incredibly small, but Michelson believed he could detect it. He teamed up with Edward Morley, a chemist at what is now Case Western Reserve University in Cleveland, and together they built one of the most famous experimental apparatuses in the history of physics. The Michelson-Morley experiment, conducted in 1887, used an interferometer, a device that splits a beam of light into two perpendicular paths, bounces them off mirrors, and recombines them. If the two beams travel at even slightly different speeds, the light waves will be out of sync when they recombine, and you'll see an interference pattern, dark and light fringes, that shift as you rotate the apparatus. The whole setup was mounted on a massive stone slab floating in a pool of mercury to isolate it from vibrations, and they could rotate it smoothly to test different orientations relative to the Earth's motion. They expected to see the fringes shift. They saw nothing, or rather, they saw shifts so small they were within the margin of error, essentially zero. They repeated the experiment at different times of day, different times of year, different orientations. Nothing. The speed of light was the same in every direction, regardless of how the Earth was moving. The ether wind they were looking for simply wasn't there. Now, This was deeply troubling. If you're riding in a boat on a river, you can definitely tell the difference between going upstream and downstream. If the Earth is plowing through an ether at 30 kilometers per second, you should be able to detect it. And they couldn't. The result was so surprising that Michelson himself considered the experiment a failure. He'd set out to measure the speed of the Earth through the ether, and instead, he'd gotten a null result. He was actually quite disappointed. But here's the thing. That null result turned out to be one of the most important experimental findings in the history of physics, because it meant one of two things. Either the ether existed, but had some bizarre property that made it undetectable. Various physicists proposed increasingly convoluted explanations, like the idea that objects contract slightly in the direction of motion, which was actually proposed by George Fitzgerald and Hendrik Lorentz, or the ether simply didn't exist, and light didn't need a medium at all. It took Einstein to cut through the confusion. In 1905, in his special theory of relativity, he simply took the Michelson-Morley result at face value. The speed of light is the same for all observers, regardless of their motion. Period. No ether needed. Light is an electromagnetic wave, oscillations of electric and magnetic fields. And those fields don't need a substance to oscillate in. They are the substance, in a sense. They propagate through empty space just fine. And this is the key distinction that makes space so quiet for sound, but so loud for light. Sound is a mechanical wave. It's the physical movement of matter, molecules pushing against each other, compression and rarefaction, a chain of collisions. No matter, no sound. But light is an electromagnetic wave. It's a self-propagating disturbance in the electromagnetic field, and that field exists everywhere, even in a perfect vacuum. So light crosses the void effortlessly. It's been doing it for 13.8 billion years, since the first photons broke free from the primordial plasma a few 100,000 years after the Big Bang. And this means the universe is anything but quiet if you have the right instruments. Every star is broadcasting. Every galaxy is a beacon. The cosmic microwave background, that faint glow left over from the early universe, fills every cubic centimeter of space. Radio waves from pulsars, X-rays from black holes devouring matter, gamma rays from the most energetic explosions in the cosmos. It's all pouring through the vacuum right now, right through you, right through the walls of whatever room you're in. You're bathed in it. You just can't hear it, because hearing is the wrong sense for the job. Your ears evolved to detect pressure waves in air, and the universe doesn't communicate that way across the void. But there's another channel, one that was only confirmed very recently, and it's arguably even more remarkable than electromagnetic radiation. Because in 2015, something happened that physicists had been waiting nearly 100 years for. Two detectors, one in Louisiana and one in Washington state, separated by about 3,000 kilometers, simultaneously detected a signal so faint that it represented a change in distance smaller than 1/10,000th the diameter of a proton. And that signal was the sound, if you want to call it that, of two black holes colliding over 1 billion light-years away. Not sound in the traditional sense, not pressure waves in a medium, but gravitational waves, ripples in the fabric of space-time itself. And the story of how we got to that detection, the decades of frustration and near failure and sheer stubborn persistence that made it possible, that's something worth talking about. Because LIGO didn't just appear out of nowhere. It wasn't some overnight success. It was one of the most ambitious, expensive, and controversial physics experiments ever attempted. And for most of its life, a lot of very smart people thought it would never work. The idea goes back to the 1960s. A physicist at the University of Maryland named Joseph Weber decided he was going to try to detect gravitational waves. Now, Einstein had predicted these waves back in 1916, just a year after publishing General Relativity. The math said that when massive objects accelerate, when stars orbit each other, when black holes merge, when neutron stars collide, they should send ripples propagating outward through space-time at the speed of light. Think of it like dropping a stone into a pond, except the pond is the fabric of the universe itself. The ripples stretch and squeeze space as they pass through. Everything in their path gets slightly compressed in one direction and slightly stretched in the perpendicular direction. Then the reverse, oscillating back and forth as the wave passes. But here's the thing Einstein himself pointed out. These ripples would be unimaginably tiny by the time they reached us from any astrophysical source. He actually doubted they could ever be detected. The effect was just too small, and for decades, most physicists agreed with him. Gravitational waves were a beautiful prediction of the theory, but they were considered a theoretical curiosity, not something you could actually go out and measure. Weber disagreed, and he was a fascinating character. He'd served in the Navy during World War II, survived the sinking of the aircraft carrier Lexington at the Battle of the Coral Sea in 1942, and later became an electrical engineer before switching to physics. He was tough, independent-minded, and not easily discouraged. In the early 1960s, he built what became known as Weber bars, large aluminum cylinders about 2 meters long and 1 meter in diameter, weighing several tons. The idea was that a passing gravitational wave would make the bar vibrate ever so slightly, like a tuning fork being struck by the faintest possible tap. He attached piezoelectric sensors to the surface to detect those vibrations. And in 1969, Weber announced that he had detected gravitational waves. He said he was seeing coincident signals between 2 bars, one at the University of Maryland and one at Argonne National Laboratory near Chicago, about 1,000 kilometers apart. The physics community was electrified. If true, this was one of the most important experimental results of the 20th century. But then, other groups tried to replicate his results. They built their own Weber bars, some even more sensitive than his, and they found nothing. Group after group, nothing. The signals Weber was seeing didn't show up in anyone else's detectors. And the theoretical calculations made it even worse. For Weber's bars to be ringing the way he claimed, the gravitational wave sources would have had to be so powerful and so frequent that they would have been converting more mass into gravitational wave energy than the galaxy actually contained. The numbers just didn't add up. It was a painful episode. Weber refused to back down. He continued to insist he was detecting real signals for the rest of his career, right up until his death in 2000. Most physicists concluded that he was wrong, that he was seeing instrumental noise and unconsciously selecting the data that confirmed what he wanted to find. It's a cautionary tale about confirmation bias in experimental physics, and it's worth treating with some compassion because Weber was a genuine pioneer. He was the first person to seriously try to detect gravitational waves, and even though his claimed detections weren't real, the work he did inspired the next generation of physicists to ask, okay, if Weber bars aren't sensitive enough, what would be? And that question led to an entirely different approach, laser interferometry. The basic concept had been floating around since the early 1960s, but it was a physicist named Rainer Weiss at MIT who really worked out the details. In 1972, Weiss published a remarkable paper. It was actually an internal MIT report, a quarterly progress report for a research contract, which is a wonderfully unglamorous origin for one of the most important ideas in modern physics. In that report, he laid out the complete design for a laser interferometer gravitational wave detector, including an exhaustive analysis of every noise source he could think of and how to deal with each one. Here's how the basic concept works, and it's beautifully simple in principle, even though it's nightmarishly difficult in practice. You take two long tubes, arranged in an L shape, perpendicular to each other. At the corner of the L, you place a laser and a beam splitter, a partially silvered mirror that splits the laser beam into two beams, sending one down each arm. At the far end of each arm, you hang a mirror. The beams travel down the arms, bounce off the mirrors, and come back to the beam splitter, where they recombine. Now, if both arms are exactly the same length, the two returning beams interfere with each other in a very specific way. You can set it up so they cancel each other out perfectly, producing darkness at the detector. But if a gravitational wave passes through, it stretches one arm and compresses the other. The lengths change by different amounts. The beams travel slightly different distances, and when they recombine, they no longer cancel perfectly. A tiny bit of light leaks through to the detector. That tiny bit of light is your signal. The elegance is that you're using light itself as your ruler. You're measuring changes in distance by watching how light waves interfere with each other, and the sensitivity you need is absolutely staggering. For a gravitational wave from a pair of merging black holes a billion light-years away, the change in arm length is about 1/10,000th the diameter of a proton. That's not a typo. The arms of LIGO are 4 kilometers long, and the change you're looking for is about 10 to the minus 19 meters. To put that in perspective, if you scaled the LIGO arm up to the distance from the Earth to the nearest star, 4 light-years away, the change you'd need to detect would be about the width of a human hair. That's the level of precision we're talking about. Weiss understood all of this in 1972. He knew exactly how sensitive the detector needed to be, and he knew exactly how hard it would be. Every possible source of noise, seismic vibrations from the ground, thermal vibrations in the mirrors, fluctuations in the laser light, even the random quantum fluctuations of the photons themselves, all of it would produce signals far larger than the gravitational wave signal you were looking for. The entire project was essentially an exercise in noise reduction on a scale that had never been attempted before. And this is where the human drama really kicks in, because building LIGO required not just brilliant physics, but also an extraordinary amount of institutional willpower, political maneuvering, and sheer stubbornness. Weiss at MIT found a kindred spirit in Kip Thorne at Caltech. Thorne was a theorist, one of the world's leading experts on general relativity, and he became convinced that gravitational wave detection was not only possible, but essential. In the late 1970s, Thorne recruited a Scottish experimental physicist named Ronald Drever to Caltech to lead the experimental effort there. And then things got complicated. Weiss and Drever were both brilliant, both passionate, and both absolutely certain that they knew the right way to build the detector. They clashed, not politely, not quietly, but fiercely and repeatedly. Drever was known for his extraordinary physical intuition and his ability to come up with clever optical tricks, but he was also, by many accounts, difficult to work with, resistant to management, and prone to changing his mind about the design. Weiss was more systematic, more methodical, and increasingly frustrated by what he saw as Drever's unwillingness to commit to a plan and stick with it. The National Science Foundation, which was being asked to fund this enormously expensive project, was watching this interpersonal chaos with growing alarm. By the mid-1980s, the NSF essentially told MIT and Caltech that they needed to get their act together, appoint a single director, create a unified project, or the funding would dry up. The result was the formal creation of LIGO, the Laser Interferometer Gravitational Wave Observatory, in 1984. But the leadership problems didn't go away. The first director lasted only a couple of years before the internal conflicts became unmanageable. Then, in 1994, the NSF and Caltech made a decisive move. They brought in Barry Barish, a particle physicist with extensive experience managing large-scale experiments. Barish had no background in gravitational waves, but he knew how to run a big project. He reorganized LIGO from what had been essentially a collection of individual research groups into a proper large-scale physics collaboration with clear management structures, milestones, and accountability. Some of the original researchers resented this. Drever, in particular, was eventually pushed out of the project entirely, which was a bitter and painful process. But Barish's organizational skills were exactly what the project needed to survive, and survival was not guaranteed. LIGO was expensive, ultimately costing over $1 billion, making it the most expensive project the NSF had ever funded, and for years it detected nothing. The initial version of the detector, called Initial LIGO, operated from 2002 to 2010 and saw no gravitational waves. This was not unexpected. The sensitivity of Initial LIGO was designed to be a proof of concept, to demonstrate that the technology worked, with the understanding that a major upgrade would be needed to reach the sensitivity where detections were likely. But 8 years of null results on a $1 billion experiment tested everyone's patience. Critics pointed out that you could fund an awful lot of other science for that money. The upgrade, called Advanced LIGO, took 5 years. New mirrors, new suspensions, new laser systems, new seismic isolation, practically everything was replaced or improved. The mirrors alone are extraordinary objects. 40 kilograms of ultra-pure fused silica, polished to a smoothness of about 1 nanometer, a few atoms. They're suspended on 4-stage pendulum systems made of fused silica fibers thinner than a human hair, designed to isolate them from ground vibrations so effectively that at the frequencies LIGO cares about, the mirrors are essentially floating in space. The laser light bounces back and forth inside the arms about 280 times before recombining, effectively multiplying the 4-kilometer arm length to about 1,120 kilometers. Every single component was engineered to suppress noise to levels that would have seemed physically impossible a generation earlier. And on September 14th, 2015, just 2 days after Advanced LIGO was switched on for its first observing run, 2 days, the detectors picked up a signal. It was 5:51 in the morning, Eastern Time. Nobody was even watching the data live. An automated system flagged it. The signal was a characteristic chirp, a wave that started low and slow, then rapidly increased in both frequency and amplitude before cutting off abruptly. It lasted about 0.2 of a second. When the team analyzed it, the signal matched the theoretical prediction for 2 black holes, one about 36 times the mass of the Sun, and the other about 29 times, spiraling into each other and merging into a single black hole of about 62 solar masses. If you do the arithmetic, you'll notice that 36 plus 29 is 65, not 62. The missing 3 solar masses, 3 times the mass of our entire Sun, had been converted into pure gravitational wave energy in a fraction of a second. For a brief moment, that collision was radiating more energy than all the stars in the observable universe combined. Think about that. Just let that settle for a moment. 3 suns worth of mass converted entirely into ripples in the shape of space, propagating outward at the speed of light, stretching and squeezing everything they pass through by an amount so small that it took the most sensitive instrument ever built by human beings to detect it, after traveling for over 1 billion years. And those ripples passed through you, through the earth, through everything, and the only trace they left was a fleeting, almost imperceptibly tiny wobble in the distance between 2 mirrors hanging in vacuum chambers in Louisiana and Washington State. Now, I called these gravitational waves sound earlier, and I put a caveat on it, but it's worth exploring why that analogy is so tempting and where it breaks down. Because when LIGO detects a signal from merging black holes, the frequencies happen to fall right in the range of human hearing, roughly 35 to 250 hertz for that first detection. If you take the raw data, the strain signal, and just pipe it into a speaker, you can actually hear it. It sounds like a quick rising tone, a whoop, and physicists genuinely call it a chirp. There are recordings of it online, and they're genuinely eerie to listen to. There's something primal about hearing that rising pitch, that accelerating sweep, knowing that what you're hearing is the translation of 2 black holes death spiraling into each other over 1 billion light years away. It feels like sound. It really does. And scientists themselves lean into the metaphor. They talk about the ring down after the merger, which is the newly formed black hole settling into its final shape, vibrating like a struck bell. A bell. That's a sound metaphor right there, used by the very people who understand better than anyone that this isn't actually sound. So where does the analogy break down? Well, here's the thing. Sound, real sound, is a mechanical pressure wave. It needs stuff. Molecules, atoms, some kind of medium, bumping into each other in sequence, passing energy along like a chain of dominoes. We spent a lot of time on that earlier, right? That's the fundamental thing. No medium, no sound. Gravitational waves are completely different in their nature. They're not pressure variations in a medium. They're distortions of space-time itself. The fabric of reality is doing the waving. There's no chain of dominoes. There's no substance being compressed and rarefied. Space itself is stretching and squeezing, and it does that perfectly well in a vacuum. In fact, it does it best in a vacuum, because there's nothing in the way. So when LIGO converts that gravitational wave signal into an audio file, what's really happening is a translation. It's like taking temperature data from a weather station and mapping it to musical notes. You can do it, and the result might sound interesting, and it might even reveal real patterns, but nobody would say the weather is making music. The gravitational wave chirp is data sonification. The frequencies happen to overlap with human hearing by coincidence, or really, by the fact that stellar mass black hole mergers happen to produce signals in that frequency range, and human ears happen to be sensitive to roughly 20 to 20,000 hertz, and there's an overlap. But the gravitational wave isn't vibrating air. It isn't vibrating anything, in the way we normally mean. It's oscillating the geometry of space. And yet, I want to be fair to the analogy, because it's not completely hollow. There is a real mathematical similarity between how sound waves propagate and how gravitational waves propagate. Both are wave phenomena. Both have frequency, amplitude, wavelength. Both carry energy. Both can interfere with each other constructively and destructively. The equations that describe them share a family resemblance. They're both solutions to wave equations, just in very different contexts. So when a physicist says, "We heard the universe," they're being poetic, but they're not being dishonest. They're pointing at something real. That gravitational waves are a signal, a carrier of information, a way the universe communicates what's happening out there. It's just that the communication channel is fundamentally different from sound. And this is actually a beautiful place to pause and think about what silence in space really means, because we've now laid out the three main ways information travels through the cosmos. You've got electromagnetic radiation, light, radio waves, X-rays, all of that, which travels perfectly well through vacuum because it doesn't need a medium. You've got gravitational waves, which are distortions of space-time itself and also travel through vacuum beautifully. And then you've got sound, good old mechanical sound, which simply cannot make the journey. It's the one channel that's blocked. Space is flooded with electromagnetic signals. Space is crisscrossed with gravitational waves from every merger, every explosion, every accelerating mass in the universe. But sound? Sound stops at the edge of every atmosphere, every gas cloud, every thin shell of matter surrounding every world. It's local. It's intimate. It belongs to places where stuff exists close enough together to touch. There's something almost poignant about that, if you think about it. The universe is incredibly communicative. It's blazing with light, trembling with gravitational waves, absolutely saturated with information. But it's silent. Not because nothing is happening, but because the particular way that we, as biological creatures, evolved to sense our immediate environment, through pressure waves in air hitting a membrane in our ears, that particular method just doesn't work across the void. Our ears are tools for navigating a world with an atmosphere. They're hyperlocal instruments, and space is the opposite of local. Now, this raises a question that I think is really fun to sit with. If you were floating in space, let's say in a spacesuit out on a spacewalk, how quiet would it actually be? Because the answer is more complicated than you might think. The obvious answer is totally silent, because there's no air to carry sound. And that's true for external sounds. If someone were next to you banging a drum and there were no air between you and the drum, you would hear absolutely nothing from it. The drum would vibrate. It would push against the thin gas molecules immediately around it if there were any. But in hard vacuum, those vibrations have nowhere to go. They can't reach you. But here's what's interesting. You wouldn't experience pure silence. You'd hear yourself. You'd hear your own breathing, loud and close, because the air inside your suit is a perfectly good medium for sound. You'd hear your heartbeat, maybe, the way you can hear it when you plug your ears. You'd hear the fans and pumps of your life support system, because those vibrations would travel through the structure of the suit and into the air inside it. Astronauts on spacewalks report this. It's not silence exactly. It's a strange, enclosed, mechanical soundscape, all generated from within. The universe outside your visor is utterly, completely mute. But your own little bubble of air is humming and hissing and thumping with the sounds of keeping you alive. And that actually connects to something that confused people for a long time about sound in space, which is the question of whether sound can travel through solids and liquids in space, even if it can't travel through the vacuum between objects. And the answer is absolutely yes. Sound doesn't care whether the medium is on Earth or in orbit or 1 billion miles from the nearest star. If you have a solid structure, say the hull of the International Space Station, sound travels through it beautifully. Vibrations from one module propagate through the metal into adjacent modules. Astronauts on the ISS actually deal with significant noise problems. The station is full of fans, pumps, compressors, experiment equipment, all generating vibrations that travel through the air inside the station and through the structure itself. Sleep can be difficult up there. They wear earplugs. NASA has had to implement noise regulations and redesign equipment to bring sound levels down because prolonged exposure to the background noise was affecting crew health and performance. So even in space, sound exists. It just exists only inside things. Inside the ISS. Inside a spacesuit. Inside the body of a comet, if you want to get exotic about it. The European Space Agency's Rosetta mission, which rendezvoused with Comet 67P/Churyumov-Gerasimenko in 2014, carried an instrument that detected oscillations in the magnetic field around the comet, and when those oscillations were shifted up in frequency and played as audio, they produced this haunting, warbling tone that the press immediately called the song of the comet. And again, this is sonification, not actual sound. The original oscillations were at frequencies far below human hearing, around 40 to 50 millihertz, and they were magnetic field variations, not pressure waves. But the impulse to turn space data into sound, to make the universe audible, is so strong that we keep doing it. We keep translating. And honestly, there's real scientific value in doing so. Our ears are remarkably good at detecting patterns. Sometimes a scientist will look at a data set visually and miss something. But when the same data is converted to audio, a rhythmic pattern or an anomaly jumps right out. There's a whole field of this, sonification as a research tool. And it's been applied to everything from solar wind data to seismic readings from Mars. NASA's InSight lander, which touched down on Mars in November 2018, carried a seismometer that detected Marsquakes, and when those seismic signals were sped up and played as audio, you could hear the planet ringing. Mars, vibrating from internal geological activity, translated into something your ears could process. It's not sound in the way you'd hear a dog bark or a car horn, but it's real physical vibration in a real solid medium, the body of Mars itself, converted into something we can experience. This is actually where things get philosophically interesting, and I want to linger here for a moment, because it connects back to something fundamental about what sound even is. We started this whole journey with the idea that sound is a pressure wave in a medium, and that's the physics definition, and it's correct. But there's another way to think about sound, which is as a perceptual experience, something that happens in your brain when your auditory system processes certain kinds of input. And by that definition, the LIGO chirp is sound because you genuinely hear it when it's played through speakers. The comet's song is sound because it enters your ears and your brain processes it as an audible tone. The Marsquake recording is sound. They're all real auditory experiences, even though the original phenomena weren't acoustic. So, is space silent? By the strict physics definition. Is there sound propagating through the vacuum between stars? No, absolutely not. The vacuum is the ultimate sound barrier. But is the universe quiet? Is there nothing to hear? That's a very different question, and the answer is no. The universe is roaring with activity. It's just communicating through channels that our ears weren't built to receive directly. We need translators, radio dishes, gravitational wave detectors, magnetometers, seismometers, to pick up those signals and convert them into something our biology can handle. And this brings us to something I find really fascinating, which is how our understanding of what counts as hearing the universe has expanded over time, and how that expansion maps almost perfectly onto the history of astronomy itself. Because for most of human history, astronomy was purely visual. You looked up, you saw stars, you tracked planets, you watched eclipses. Everything we knew about the cosmos came through one narrow band of the electromagnetic spectrum, visible light, because that's what our eyes could detect. And then, in the early 20th century, something changed. A young engineer named Carl Jansky, working at Bell Telephone Laboratories in Holmdel, New Jersey, stumbled onto something that would open up an entirely new window on the cosmos. It was 1931, and Jansky was 26 years old, fresh out of the University of Wisconsin with a physics degree, and Bell Labs had given him a pretty specific assignment. They wanted him to figure out what was causing static on transatlantic radio telephone calls. That's it. That was the job. Not glamorous, not cosmic, just find the noise and figure out how to get rid of it. So Jansky built this antenna, and it was a beautifully strange contraption, this thing. It was about 100 feet long and 20 feet tall, made of brass pipes and wooden 2x4s, mounted on a set of Ford Model T wheels and tires so it could rotate. The whole apparatus turned slowly, making one full rotation every 20 minutes, which earned it the nickname Jansky's merry-go-round. And he sat there in Holmdel, in the fields of central New Jersey, slowly spinning this antenna, around and around, listening to the sky at a frequency of about 20.5 megahertz, which is around 14.6 meters wavelength, and he cataloged everything he heard. He found 3 types of static. The first 2 made perfect sense: nearby thunderstorms and distant thunderstorms. Lightning produces radio waves, and those radio waves propagate through the atmosphere and show up as crackles and pops in your receiver. No mystery there. But the third type of static was different. It was a steady, gentle hiss, not sharp like lightning, not intermittent. Just this persistent, faint whisper of radio energy that seemed to come from a fixed direction in the sky. And here's what was clever about Jansky's approach. Because his antenna rotated, he could track where the signal was strongest. And at first, he thought it was coming from the sun, which would make sense, right? The sun is this enormous nuclear furnace. You'd expect it to be blasting out radio waves. But as he tracked the signal over weeks and months, he noticed something. The peak of the signal wasn't keeping pace with the sun. It was drifting. It was arriving about 4 minutes earlier each day, which, if you know a little astronomy, you'll recognize as the difference between a solar day and a sidereal day. The time it takes Earth to rotate once relative to the distant stars versus relative to the sun. That 4-minute drift told Jansky that the signal wasn't coming from the sun. It was coming from something much farther away. It was coming from the stars. More specifically, when he mapped the direction of the strongest signal, it pointed toward the constellation Sagittarius, which is where the center of our Milky Way galaxy lies. Jansky had accidentally discovered that the galaxy itself was emitting radio waves. He published his results in 1933, and the New York Times ran a front-page story about it. For a brief moment, the world paid attention, and then mostly moved on. The astronomical community was polite, but largely uninterested. Jansky himself wanted to build a bigger antenna, a proper dish, to study these cosmic radio emissions in more detail, but Bell Labs said no. They'd gotten what they needed. They knew what was causing the static, and it wasn't something they could fix. So from their perspective, the project was done. Jansky moved on to other work. He died in 1950, at just 44, from a heart condition he'd struggled with most of his life. He never got to build that bigger antenna, but someone else did. And this is one of my favorite stories in the history of science, because it involves a person who, by all conventional measures, had no business making a major astronomical discovery. His name was Grote Reber, and he was a radio engineer from Wheaton, Illinois, an amateur, a backyard tinkerer. He'd read Jansky's papers and was fascinated, And when he realized that no professional astronomer was following up on the discovery, he decided he'd do it himself. So in 1937, in his mother's backyard, Reber built a parabolic radio dish. By hand. It was about 31 feet across, made of sheet metal, and it was the first purpose-built radio telescope in the world. His neighbors must have thought he was absolutely out of his mind. This enormous metal structure looming over the yard, and Reber out there night after night, scanning the sky, mapping the radio emissions from the Milky Way. And he confirmed and extended everything Jansky had found. He produced the first radio frequency sky maps, showing that the strongest emissions came from the galactic center and from other regions along the plane of the Milky Way. He published in the Astrophysical Journal, which was remarkable for a non-academic working alone in suburban Illinois. For nearly a decade, from the late 1930s into the mid-1940s, Grote Reber was essentially the only radio astronomer on Earth. One guy, one dish, one backyard. Think about that for a second. An entire field of science carried on the shoulders of one stubborn, curious amateur who just couldn't let the question go. Now, the reason I'm telling you this story in such detail is because it perfectly illustrates something about how we've expanded our ability to hear the universe. Jansky and Reber didn't detect sound. Radio waves are electromagnetic radiation. They travel through vacuum just fine at the speed of light, no medium required. They're in the same family as visible light, just at much longer wavelengths. But here's the thing. The experience of working with radio astronomy feels like listening. You're not looking at anything. You're pointing a receiver at the sky and picking up signals. The data comes in as patterns of intensity over time and frequency, and the natural metaphor is auditory. Radio astronomers even talk about listening to the sky. The language of sound permeates the field, even though the physics is entirely electromagnetic. And this matters for our story about the silence of space, because it shows how humans have systematically found ways to perceive what the vacuum would otherwise hide from us. Visible light was our first channel. Radio waves became the second. And once that door opened, it swung wide. After World War II, the technology that had been developed for radar, all those advances in sensitive receivers, antenna design, signal processing, suddenly became available for scientific use, and radio astronomy exploded. Suddenly there were groups in England, in the Netherlands, in Australia, all building radio telescopes and making discoveries that optical astronomers had never dreamed of. In 1967, a graduate student named Jocelyn Bell, working with her advisor Anthony Hewish at Cambridge, discovered pulsars, rapidly rotating neutron stars that emit beams of radio waves like cosmic lighthouses. The signal was so regular, so precise, that they initially half-jokingly labeled it LGM1 for little green men, because they couldn't imagine a natural source that could pulse with such clockwork regularity. The pulses came every 1.337 seconds, every single time, with a precision that rivaled the best atomic clocks. And when Bell and Hewish figured out what was actually producing the signal, a neutron star, the collapsed core of a dead massive star, spinning on its axis and sweeping a beam of radio emission across Earth with each rotation. It was one of those moments where the universe turns out to be stranger and more wonderful than anyone had imagined. Hewish won the Nobel Prize for it in 1974, though many people felt then, and feel now, that Bell should have shared it. She'd done the painstaking work of analyzing miles of chart recorder paper. She'd spotted the anomalous signal. She'd fought to investigate it when others wanted to dismiss it as interference. It's one of those stories that still stirs debate. But the point is, pulsars are another example of the universe communicating through a channel that isn't sound, but that we experience in profoundly auditory ways. When you speed up pulsar recordings, they sound like heartbeats, like ticking clocks, like drum rolls. The fastest pulsars, the millisecond pulsars, spin hundreds of times per second, and when you play their signals through a speaker, they produce a tone, a musical note. There's one called PSRB 1937 plus 21 that spins 641 times per second, which if you converted that rotation rate directly to an audio frequency, you'd get a note somewhere around a high C sharp. The universe is full of rhythms and frequencies that map beautifully onto our sense of hearing, even though no actual sound wave is involved. And this is where I want to circle back to something we touched on earlier, the idea that the universe is roaring with activity, just in languages our ears can't natively understand. Because as the 20th century progressed, astronomers kept opening new windows. After radio came infrared astronomy, then ultraviolet, then X-ray and gamma-ray astronomy. Each new wavelength revealed objects and phenomena that were completely invisible in other bands. Some of the most violent events in the universe, gamma-ray bursts, for instance, are almost invisible in optical light, but blindingly bright in gamma rays. If you only had eyes, you'd never know they were happening. The universe would seem quieter and calmer than it actually is. And here's what's really beautiful about this progression. Each new observational window required engineering solutions to a fundamental problem. Earth's atmosphere blocks most of the electromagnetic spectrum. Visible light gets through. Radio waves mostly get through. But infrared is largely absorbed by water vapor. Ultraviolet is blocked by the ozone layer, and X-rays and gamma rays are stopped dead by the upper atmosphere. So to observe in those wavelengths, you have to get above the atmosphere. You have to go to space, which means the history of expanding our cosmic hearing is also the history of spaceflight, of rocketry, of building instruments tough enough to survive launch and precise enough to do science in orbit. The first X-ray source outside the solar system was discovered in 1962, when a team led by Riccardo Giacconi launched a small detector on an Aerobee-sounding rocket from White Sands, New Mexico. The rocket flew for about 6 minutes above the atmosphere, and in that brief window, the detector picked up a powerful X-ray source in the constellation Scorpius. Scorpius X1, it was called. Giacconi would eventually win the Nobel Prize for his pioneering work in X-ray astronomy, and the field would grow to include orbiting observatories like the Chandra X-ray Observatory, which, and this brings us full circle in a satisfying way, is the very same telescope that Andrew Fabian used to detect those sound waves rippling through the Perseus cluster. The same instrument that gave us the deepest note ever detected in the universe, that B-flat 57 octaves below middle C. So there's this thread running through the whole story, from Jansky's merry-go-round in New Jersey, to Reber's backyard dish, to Bell's pulsars, to Giacconi's 6-minute rocket flight to Chandra, orbiting high above the atmosphere. And the thread is this. Every time we build a new kind of detector, every time we figure out how to sense a form of energy we couldn't sense before, the universe gets louder. Not louder in the acoustic sense. The vacuum is still there, still blocking sound waves as absolutely as it ever did. But louder in the sense that we can perceive more of what's actually happening out there. The silence of space starts to feel less like emptiness and more like a translation problem. And that translation problem is something that modern astronomers think about a lot, actually. because we're living through another one of those moments where a brand new observational window is opening up. We talked about LIGO and gravitational waves, and that's one. But there's another channel that's even more ghostly, even harder to detect, and it involves a particle so elusive, so reluctant to interact with ordinary matter, that trillions of them are passing through your body right now, right this second, without touching a single atom. I'm talking about neutrinos, and the story of how we learned to detect neutrinos and what they can tell us about the most violent events in the universe is one of the most remarkable detective stories in all of physics. So let's start with what a neutrino actually is. Picture the sun. You know, it's a giant nuclear furnace, right? Deep in its core, hydrogen atoms are being fused together into helium at temperatures around 15 million degrees. That fusion process releases energy. That's what makes the sun shine. That's the warmth on your face on a summer afternoon. But the fusion reactions don't just produce light. They also produce these tiny, almost massless particles called neutrinos. And when I say almost massless, I mean it. A neutrino weighs so little that for decades physicists weren't even sure it had any mass at all. It's electrically neutral, which means it doesn't respond to electromagnetic forces. It doesn't respond to the strong nuclear force that holds atomic nuclei together. The only forces it really feels are gravity, which barely matters because it's so light, and the weak nuclear force, which is, as the name suggests, weak. And because of that, neutrinos almost never interact with anything. They're produced in the core of the sun, and while photons, particles of light, take something like 100,000 years to bounce and scatter their way from the sun's core to its surface, neutrinos just fly straight out. They leave the core at nearly the speed of light, and they're gone. 2 seconds later, they're past the sun's surface. 8 minutes after that, they're hitting Earth. And by hitting, I mean passing through, because they go right through the entire planet without noticing it's there. About 65 billion solar neutrinos pass through every square centimeter of your skin every second. Every second. And essentially, none of them interact with you at all. Now, the existence of the neutrino was predicted before it was ever detected, and the story of that prediction is wonderful. It starts in the 1920s with a problem in nuclear physics. Scientists were studying a type of radioactive decay called beta decay, where a neutron inside, an atom, transforms into a proton and spits out an electron. The trouble was, the energy didn't add up. You'd measure the energy of the electron coming out, and it was always less than it should have been. Energy was going missing. And this was deeply troubling, because conservation of energy is one of the most fundamental principles in all of physics. Some very serious people, Niels Bohr among them, were actually willing to consider that maybe conservation of energy just didn't hold at the subatomic level. Maybe the rules broke down. That's how desperate things were. But in 1930, Wolfgang Pauli proposed a different solution. He suggested that there was another particle being emitted in beta decay, one that carried away the missing energy, but that was so hard to detect that nobody had ever seen it. He called it the neutron at first, but that name got taken by a different particle a couple of years later, so Enrico Fermi gave Pauli's particle the name neutrino, the little neutral one, in Italian. And Pauli was almost apologetic about the idea. He famously wrote in a letter that he had done a terrible thing. He had postulated a particle that could not be detected. He said he had committed something that no theoretical physicist should ever do. But here's the thing. He was wrong about it being undetectable. It just took 26 years. In 1956, two physicists named Clyde Cowan and Frederick Rhines finally caught a neutrino, and the way they did it is beautifully clever. They set up their experiment next to a nuclear reactor at the Savannah River site in South Carolina. A nuclear reactor, like the Sun, produces enormous numbers of neutrinos through fission reactions. So Cowan and Rhines positioned a large tank of water laced with cadmium chloride right next to the reactor, surrounded by scintillation detectors, devices that produce tiny flashes of light when a particle interacts with them. The idea was that very, very occasionally, a neutrino from the reactor would strike a proton in the water and produce a neutron and a positron. The positron would immediately annihilate with a nearby electron, producing two gamma rays going in opposite directions. Then, microseconds later, the neutron would be captured by a cadmium nucleus, producing another burst of gamma rays. So you'd get this distinctive double flash, two signals separated by a specific tiny time delay. That was your neutrino signature, and they found it. They actually saw it. Rhines eventually won the Nobel Prize for this work in 1995, though sadly Cowan had passed away by then. So now we knew neutrinos were real, and we could detect them, at least in principle. But detecting neutrinos from space, from the sun, from distant stars, from cosmic explosions, that was a whole different challenge. The reactor was right there, blasting out neutrinos from just meters away. The sun is 93 million miles away. You needed a much bigger detector, and you needed to shield it from every other kind of particle and radiation so that only neutrinos could reach it. This is where a chemist named Ray Davis comes in, and his story is one of the most patient, stubborn pursuits in the history of science. In the mid-1960s, Davis built a neutrino detector deep underground in the Homestake Gold Mine in Lead, South Dakota. Nearly a mile underground, because that much rock filters out almost everything. Cosmic rays, muons, all the noisy particles raining down from the atmosphere. The only things that could penetrate that deep were neutrinos. His detector was a tank containing about 100,000 gallons of perchloroethylene, dry cleaning fluid basically. The idea, based on a suggestion by the theorist Bruno Pontecorvo, was that when a neutrino interacted with a chlorine atom in the fluid, it would transform it into an atom of argon. So every few weeks, Davis would carefully extract the argon atoms from this enormous tank of cleaning fluid, count them, and that count would tell him how many neutrinos had been captured. Think about what that means for a second. He's looking for a handful of atoms, literally a few dozen atoms of argon, in 100,000 gallons of liquid. It's like searching for a specific grain of sand on a beach, except the beach is underground, and the grain of sand was put there by a ghost. The precision required was extraordinary. And when Davis started getting results in the late 1960s, something was wrong. He was detecting neutrinos from the sun, which was wonderful. It was the first direct confirmation that nuclear fusion was actually happening in the sun's core, which is remarkable when you think about it. But he was only detecting about a third as many neutrinos as the theoretical models predicted. The models said he should be catching a certain number per month, and he was consistently getting fewer, way fewer. This became known as the solar neutrino problem, and it haunted physics for over 30 years. Was Davis's experiment wrong? Were the solar models wrong? Was something else going on entirely? Davis kept running the experiment year after year, refining his techniques, checking and rechecking. The numbers held. The deficit was real, and eventually, the answer turned out to be one of the most beautiful surprises in particle physics. Neutrinos come in three types, or flavors. electron neutrinos, muon neutrinos, and tau neutrinos. The Sun produces electron neutrinos. Davis's detector could only catch electron neutrinos. And what was happening, as Pontecorvo had actually speculated decades earlier, was that the neutrinos were changing flavor as they traveled from the Sun to Earth. They were oscillating between types. By the time they reached South Dakota, 2/3 of them had transformed into muon, or tau neutrinos, which sailed right through the cleaning fluid without a trace. This was definitively confirmed in 2001 by the Sudbury Neutrino Observatory in Ontario, Canada, a detector that could sense all 3 flavors. And it found exactly the total number of neutrinos the solar models predicted. The Sun was fine. The models were fine. It was the neutrinos themselves doing something nobody had expected. And here's the kicker. Neutrino oscillation can only happen if neutrinos have mass. Even a tiny mass, but mass nonetheless. And the original standard model of particle physics said neutrinos were massless. So this discovery, born from Ray Davis patiently counting argon atoms in a mine shaft, ended up requiring an extension of the standard model itself. Davis shared the Nobel Prize in 2002, when he was 87 years old. Now, why does all of this matter for our story about the silence of space? Because neutrinos represent yet another way the universe communicates. Another channel of information flowing through the cosmos that has nothing to do with sound waves and nothing to do with the electromagnetic spectrum. Neutrinos pass through dust clouds that block light. They escape from the cores of stars and supernovae in seconds, while light can take hours or days to fight its way out through the collapsing outer layers. They carry information from places that are literally opaque to every other form of observation. And we've actually received a message through this channel from a cosmic catastrophe. On February 23, 1987, a burst of neutrinos was detected almost simultaneously by 3 different detectors around the world: Kamiokande, 2 in Japan, the IMB detector in Ohio, and the Boxon detector in Russia. About 24 neutrinos total, arriving within a span of about 13 seconds. 24 particles, that's all. But those 24 neutrinos told us that a massive star in the Large Magellanic Cloud, a small galaxy orbiting our own about 168,000 light-years away, had just collapsed and exploded. The light from that supernova 1987A, wasn't spotted by optical telescopes until several hours later. The neutrinos arrived first because they escaped the collapsing star immediately, while the light had to wait for the shock wave to reach the star's surface. Think about what that means. The neutrinos carried news of a star's death across 168,000 light-years of space, through the vacuum, through dust, through everything, and arrived at Earth before the light did. 24 particles, and they confirmed decades of theoretical work about how stars die. They told us the core had collapsed to a neutron star. They told us about the temperatures and densities involved. 24 particles. And today, neutrino astronomy is growing. The IceCube Neutrino Observatory at the South Pole uses a cubic kilometer of Antarctic ice, 1 billion tons of ice, as its detector. Sensors are buried deep in the ice, watching for the faint blue flashes of Cherenkov radiation produced when a neutrino, on those incredibly rare occasions, interacts with a molecule in the ice. In 2017, IceCube detected a high-energy neutrino that was traced back to a blazar, a supermassive black hole shooting a jet of particles almost directly at Earth, about 4 billion light-years away. That was the first time a high-energy cosmic neutrino source was identified, and it opened yet another window. So now count the channels. We have electromagnetic radiation across the entire spectrum: radio, infrared, visible, ultraviolet, X-ray, gamma ray. We have gravitational waves, ripples in space-time itself, and we have neutrinos, ghost particles that barely interact with matter at all. Three fundamentally different ways of observing the universe, each one revealing things the others can't. Astronomers call this multi-messenger astronomy, and it's one of the most exciting developments in the field right now, because when you can observe the same event through multiple channels simultaneously, catching the gravitational waves and the neutrinos and the electromagnetic radiation from a single cataclysm, you get a picture that's incomparably richer than any single channel could provide. And there's actually a fourth channel that some physicists dream about, one that would let us see further back in time than any of the others. It involves something called the cosmic neutrino background, but even more tantalizing is the possibility of detecting primordial gravitational waves imprinted on something you've probably heard of, even if you're not sure exactly what it is: the cosmic microwave background. And to understand why that matters, we need to talk about the very early universe, the first few 100,000 years after the Big Bang, and what was happening to sound, actual, literal sound waves, in a cosmos that was so dense and so hot that it was essentially a single, roaring fluid. That's the part of the story that surprises people the most, because we've spent all this time talking about why space is quiet, why sound can't travel through the vacuum between stars, and now here we are saying that the entire universe, in its earliest phase, was actually full of sound. Real, physical, pressure-driven sound waves propagating through a medium that filled all of space. And it's true. For roughly the first 380,000 years after the Big Bang, the universe was not empty. It was not a vacuum. It was a blisteringly hot plasma, a soup of protons, electrons, photons, and a few other particles, all crammed together so tightly that light couldn't travel more than a tiny distance before smashing into something. Photons would scatter off free electrons almost immediately, the way light scatters in dense fog. The universe was opaque. You couldn't have seen anything, even if you'd had eyes to see with, because light simply couldn't get anywhere. But here's the thing: that plasma had pressure. It had density. It was a fluid in every meaningful sense, and fluids can carry sound waves. So when tiny fluctuations in density appeared, and they did appear, seeded by quantum fluctuations that got stretched to enormous scales during a brief period of exponential expansion, called inflation, those fluctuations didn't just sit there. They propagated. They moved through the plasma as acoustic waves, compressions and rarefactions, regions where the plasma was slightly denser and regions where it was slightly thinner, rippling outward at a specific speed. The speed of sound in that primordial plasma was astonishing, roughly 57% of the speed of light. Think about that for a second. Sound, traveling at more than half the speed of light. On Earth, sound moves at about 343 meters per second through air. In the early universe, it moved at about 170,000 kilometers per second. That's how different the medium was. This wasn't air, wasn't water, wasn't steel. This was a relativistic plasma where radiation pressure, the push of all those trapped photons bouncing around, provided most of the restoring force. And that radiation pressure was enormous, which is why the sound speed was so high. Now, the sound waves in the early universe weren't like anything you'd recognize as a tone or a note, at least not in the way you'd experience them. The wavelengths were cosmological. Some of these acoustic oscillations stretched across tens of thousands of light years. The frequencies, if you converted them to something we could hear, which of course you can't directly, but physicists have done the math, would be extraordinarily low. We're talking something like 50 octaves below the lowest note a human ear can detect, way, way below the threshold of hearing. But they were sound waves. They obeyed the same physics, compressions and rarefactions in a medium driven by pressure, propagating at a well-defined speed. The universe was ringing, and here's where it connects to something observable. Those sound waves didn't just vanish, they left a mark. Around 380,000 years after the Big Bang, the universe cooled enough, down to roughly 3,000 Kelvin, that protons and electrons could finally combine to form neutral hydrogen atoms. This event is called recombination, which is a slightly misleading name because it implies they were combined before, which they weren't, but the name stuck. Once the plasma became neutral gas, photons could suddenly travel freely. The fog lifted, light was released, and it's been traveling ever since, stretching and cooling as the universe expanded, until today it reaches us as a faint glow of microwave radiation coming from every direction in the sky. That's the cosmic microwave background, the CMB. It was first detected accidentally in 1965 by Arno Penzias and Robert Wilson at Bell Labs in New Jersey. They were working with a large horn antenna originally built for satellite communications, and they kept picking up a persistent hiss of microwave noise that they couldn't get rid of. They cleaned pigeon droppings off the antenna. They checked every connection. They pointed it in every direction. The noise was always there, uniform, coming from everywhere. It took a while before they connected with theorists at Princeton, who realized what Penzias and Wilson had found. The afterglow of the Big Bang itself, predicted years earlier, but never detected. They won the Nobel Prize for it in 1978. But the really beautiful part came later, when instruments got precise enough to measure not just the existence of the CMB, but its tiny imperfections. Because that microwave glow isn't perfectly uniform. It's almost uniform. The temperature is about 2.725 Kelvin everywhere you look, but there are minuscule variations on the order of 1 part in 100,000, tiny hot spots and tiny cold spots. And those variations are the fingerprints of those primordial sound waves. The acoustic oscillations that were ringing through the plasma for 380,000 years got frozen into the pattern of the CMB at the moment of recombination. It's like a snapshot of the sound field at the instant the music stopped. The compressions, regions where the plasma was slightly denser and hotter, show up as slightly warmer spots. The rarefactions show up as slightly cooler spots. And when you analyze the statistical pattern of those temperature variations, when you break them down by angular scale on the sky, you get something extraordinary. A power spectrum with a series of peaks. The first peak, the second peak, the third peak. Each one corresponding to a specific harmonic of those primordial acoustic oscillations. This is genuinely one of the most remarkable things in all of science. The universe was literally a resonating cavity, like the inside of a musical instrument, and the harmonics of that resonance are written into the oldest light we can see. The position and height of those peaks tell cosmologists an incredible amount about the universe, its geometry, its total density, how much of it is ordinary matter versus dark matter versus dark energy, even its age. The first detailed measurement of these peaks came from a balloon-borne experiment called Boomerang in 2000, and then with spectacular precision from NASA's WMAP satellite, which launched in 2001, and later from the European Space Agency's Planck satellite, which operated from 2009 to 2013. Planck measured the CMB temperature fluctuations with such exquisite accuracy that cosmologists could extract the values of fundamental cosmological parameters to within 1% or 2. And all of it, rests on understanding those sound waves in the early universe. So let's sit with that for a moment. The reason space is quiet today is that it's a vacuum. There's no medium to carry pressure waves. But the reason we know so much about the universe's composition and history is that space wasn't always a vacuum. For its first few 100,000 years, the cosmos was filled with a medium, and that medium carried sound, and that sound left permanent marks on the oldest light in existence. The silence of space today and the ancient music of the early universe are two sides of the same story. Now, about that fourth channel I mentioned, the one that some physicists dream about. The cosmic microwave background is a snapshot of the universe at 380,000 years old. That's incredibly early, but it's not the beginning. There's a whole era before recombination that the CMB can't directly show us, because before that moment, the universe was opaque to light. Photons couldn't escape. So how do you see further back? One possibility is gravitational waves. Remember, gravitational waves don't need a medium, and they don't interact with matter in the way light does. They pass through everything. If the period of cosmic inflation that occurred in the first tiny fraction of a second after the Big Bang, we're talking something like 10 to the negative 36 seconds. If inflation really happened the way most cosmologists think it did, then it should have generated a background of primordial gravitational waves. These waves would have been stretched by the expansion of the universe to enormous wavelengths, and they would have left a very specific signature in the CMB, a particular pattern of polarization called B-mode polarization. This is where it gets both exciting and cautionary. In March 2014, a team using a telescope at the South Pole called BICEP-2 announced that they had detected B-mode polarization in the CMB, and they claimed it was evidence of primordial gravitational waves from inflation. The announcement made headlines around the world. It was hailed as one of the greatest discoveries in cosmology. But within months, doubts emerged. The Planck satellite team showed that much or all of the signal BICEP-2 had detected could be explained by polarized emission from dust in our own galaxy. Tiny grains of interstellar dust that align with the galaxy's magnetic field and emit polarized microwave radiation that can mimic the inflationary signal. By early 2015, a joint analysis by the BICEP-2 and Planck teams concluded that the dust contamination was significant enough that no confident detection of primordial gravitational waves could be claimed. It was a painful episode for the researchers involved, many of whom had dedicated years of their careers to the measurement. But it was also science working exactly the way it should. A bold claim, scrutinized by the community, tested against alternative explanations, and ultimately found to be premature. The search continues, though. New experiments, BICEP-3, the BICEP Array, the Simons Observatory in Chile, and a proposed satellite mission called LIGHTBIRD, are all designed to push the sensitivity further, to separate the inflationary signal from galactic foregrounds with greater precision. If primordial gravitational waves are ever definitively detected, it would be a window into the universe at a fraction of a second old, far earlier than anything the CMB itself can show us. It would confirm that inflation happened, constrain the energy scale at which it occurred, and open a channel of information that predates the formation of atoms, predates the primordial plasma, predates essentially everything we can currently observe. That's the fourth messenger, still hypothetical, still being hunted. And And you know what's quietly astonishing about all of this? Every single channel we've talked about, every way we have of learning about the cosmos, exists precisely because space is the way it is. Electromagnetic radiation travels to us because the vacuum of space is transparent to photons. Gravitational waves reach us because space-time itself is the medium, and it extends everywhere. Neutrinos arrive because they barely interact with the matter in between. And the silence, the absence of sound in the void between stars, is what makes all of these other channels so clean, so readable. If space were filled with some dense medium, if sound could travel between the stars, the universe would actually be harder to observe, not easier. The noise would be overwhelming. The quiet is what lets us listen to everything else. There's a kind of engineering lesson buried in that, if you think about it. Sometimes the most important feature of a system isn't what it does, it's what it doesn't do. The vacuum of space doesn't carry sound, and that absence, that silence, is what makes the universe legible. It's what lets a dish antenna in New Mexico pick up the whisper of a quasar billions of light years away, or lets a laser interferometer in Louisiana detect a ripple in space-time thinner than a proton. The quiet isn't emptiness. It's something more like clarity. It's the condition that makes observation possible. Think of it like the silence in a concert hall just before the orchestra begins. Not nothing, but a prepared space, a readiness, the thing that lets every note land exactly where it should. And that metaphor actually holds up better than you might expect, because the universe really does have a kind of music to it, if you're willing to stretch the word just a little. We've spent all this time talking about why space is quiet, why sound can't travel through the vacuum, why the popular imagination of roaring explosions in space is just flat wrong. And all of that is true. But here at the end, it's worth sitting with the deeper truth, which is that the universe is anything but silent. It's just that you have to learn how to listen in the right way, with the right instruments, tuned to the right frequencies, and then it's extraordinarily loud, rich, layered, full of information, full of story. The quiet of space isn't the quiet of nothing happening. It's the quiet of a library where every book is open, every page is radiating its contents outward, and all you need is the ability to read. Let's think about where we are now, in this moment, in terms of what humanity can actually hear from the cosmos. Because the picture has changed so dramatically even in just the last couple of decades that it's worth pausing to appreciate it. When Carl Jansky stumbled onto cosmic radio waves in 1932, he opened one ear. When Grota Robert built his backyard dish and started mapping the radio sky, he proved that ear could be trained. When Jocelyn Bell noticed that bit of scruff on the chart paper in 1967, she showed us that the radio universe had a pulse, a rhythm, a regularity that hinted at physics we hadn't imagined. When Riccardo Giacconi flew that Geiger counter on a sounding rocket in 1962, he opened a completely different ear. X-rays, the high-energy scream of matter falling into black holes and neutron stars colliding. Every new wavelength we learned to detect was like gaining a new sense, a new way of perceiving something that had always been there, but that we simply couldn't access before. And then, in September 2015, LIGO heard space-time itself vibrate. That wasn't electromagnetic radiation at all. That was a fundamentally different kind of signal, carried by a fundamentally different mechanism. Not photons moving through space, but space itself stretching and compressing, rippling outward from the collision of two black holes more than 1 billion light-years away. And just 2 years later, In August 2017, LIGO and Virgo detected the merger of two neutron stars, and within seconds, the Fermi Gamma Ray Space Telescope saw a burst of gamma rays from the same patch of sky. And within hours, telescopes all over the world were swinging toward that point, watching the afterglow in visible light, in infrared, in ultraviolet, in radio. That event, GW170817, as it's catalogued, was the first time humanity observed a single cosmic event through both gravitational waves and electromagnetic radiation simultaneously. Multi-messenger astronomy went from theoretical aspiration to operational reality in the span of about 11 hours. And we'd already had a taste of multi-messenger astronomy with neutrinos, remember? SN 1987. That supernova in the Large Magellanic Cloud gave us about 24 neutrinos in the Kamiokande and IMB detectors before the light even arrived. And then IceCube, that cubic kilometer of instrumented Antarctic ice, traced a high-energy neutrino back to a blazar in 2017, adding yet another thread. So by the end of that year, 2017, humanity had three independent, fundamentally different ways of receiving information from the cosmos: light in all its wavelengths, gravitational waves, and neutrinos. Three messengers. Three completely different physics. Three channels that each tell you things the others can't. And we talked about the fourth. Those primordial gravitational waves from inflation. The ones that would be imprinted in the polarization of the cosmic microwave background as B-mode patterns. Still being searched for. Still elusive. The BICEP 2 team thought they had them in 2014, and the scientific community held its breath for a few months before the Planck satellite's dust maps showed that galactic foreground contamination could explain the signal. That was a heartbreak, honestly, for the people involved. Years of painstaking work at the South Pole, extraordinary instrumental precision, and then the realization that the universe had played a trick, that the galaxy's own dust, swirling in the magnetic fields of the Milky Way, could mimic the very signal they were looking for. But that's how science works. You don't get to choose what the data says. You just have to be honest about it and go back and try again with better tools. And they are trying again. The BICEP array is operating now, with more detectors, more frequency bands, better ability to separate the cosmic signal from the galactic foreground. The Simons Observatory in Chile's Atacama Desert is coming online, with tens of thousands of detectors designed to measure the CMB polarization with extraordinary sensitivity. And Lightbird, the Japanese-led space mission, is being developed to observe the entire sky from orbit, free from atmospheric interference, specifically targeting that primordial B-mode signal. If any of these experiments detect it, and the signal might be there, just below current sensitivity thresholds, it would be, without exaggeration, one of the most profound observations in the history of science. It would tell us about the universe at energies so high that no particle accelerator could ever reach them, energies associated with the unification of fundamental forces, energies that existed in the first tiny fraction of a second after whatever started everything. But here's what I want you to carry with you as you drift off tonight, if you're still with me. It's not just the facts, not just the dates and the names and the instruments, though I hope some of those stick. It's the shape of the story. Because the story of why space is quiet is really the story of how humanity learned to listen. We started with our ears. Literal human ears, evolved to detect pressure waves in the atmosphere of one small planet. And for most of human history, that was the only way we could perceive the universe. By looking up with our eyes, which are just biological detectors of a narrow band of electromagnetic radiation, and by listening with our ears, which heard nothing from the sky because there was nothing for sound to travel through. The sky was silent, and for thousands of years, we didn't even have the conceptual framework to understand why. We didn't know what sound was. We didn't know what a vacuum was. We didn't know that the space between Earth and the Moon was fundamentally different from the air we breathed. And then, piece by piece, we figured it out. Pythagoras and his followers noticed that the length of a vibrating string determined its pitch, and that was the first hint that sound was something physical, something measurable, something governed by rules. Centuries later, Robert Boyle put a bell in a glass jar, pumped out the air, and watched the sound disappear, and that was the proof that sound needed a medium. Newton worked out the mathematics of how pressure waves propagate. And eventually, by the 19th century, we understood that space was a vacuum, or very close to one, and that sound as we know it simply could not exist there. But we also learned that light could travel through that vacuum. And that was the crack in the door. Because once we understood that electromagnetic radiation didn't need a medium, once the Michelson-Morley experiment killed the luminiferous ether and Einstein's special relativity explained why, we realized that the vacuum wasn't a barrier. It was a highway. Photons could cross billions of light years of absolutely nothing and arrive at our detectors carrying information about where they came from, what they'd passed through, how old they were, the silence of space, the absence of any medium for sound was precisely what made that highway so clear. No interference, no absorption, no noise, just signal. And then we built bigger ears. Radio dishes and X-ray telescopes and gamma-ray satellites and neutrino detectors buried under mountains and gravitational wave observatories with laser beams bouncing back and forth in vacuum tubes 4 kilometers long. Each one a different kind of ear, listening for a different kind of whisper. And the universe, it turns out, has been whispering all along. It's been radiating, vibrating, pulsing, flashing, rippling, streaming particles in every direction. It's been doing this for 13.8 billion years. We just had to learn how to hear it. And isn't that a beautiful thought to fall asleep to? The universe isn't quiet because nothing is happening. The universe is quiet because the information it sends us travels in forms that human ears were never designed to detect. Sound is just one way that information can move through a medium, and it happens to be the way that doesn't work in space. But light works. Gravitational waves work. Neutrinos work. And maybe, someday, primordial gravitational waves imprinted on the oldest light in the universe will work too. The silence is real, but it's not the whole story. It's not even most of the story. You know, there's a recording that NASA released a few years ago, a sonification of the pressure waves in the Perseus galaxy cluster, the ones that Andrew Fabian and his team discovered back in 2003. Remember those? The ones 57 octaves below middle C, far too low for any human ear, rippling through the hot intracluster gas at the center of a galaxy cluster 300 million light-years away. NASA took that data and shifted it up into the audible range, and you can actually listen to it. It sounds eerie, deep, almost like a moan. It's not really what the cluster sounds like. That phrase doesn't quite make sense, but it's a translation, a way of rendering in sound what was originally a pattern of pressure in an unimaginably vast, unimaginably hot cloud of gas. And there's something poignant about that. We found real sound waves in space, actual acoustic oscillations in an actual medium, and they were so far below anything we could hear that we had to shift them up by a factor of hundreds of quadrillions just to perceive them. Even the sound that does exist in space is inaudible to us. The universe keeps its secrets in frequencies we were never built to notice. But we notice them anyway. That's the remarkable part. We build the instruments. We do the math. We sit with the data for years, sometimes decades, teasing out signals from noise, arguing about systematic errors, checking and rechecking. And slowly, patiently, we hear things that no ear could ever hear. We feel vibrations that no hand could ever feel. We catch particles that pass through the entire Earth without stopping. So as you lie there, wherever you are, and the room is quiet around you, and maybe the only sound is your own breathing or the hum of something electrical in the background, think about this. Right now, at this very moment, photons from the cosmic microwave background are passing through the walls, through you, through everything. They've been traveling for 13.8 billion years since the universe was a glowing fog of plasma, and they carry in their patterns the frozen echoes of sound waves that rang through the early cosmos before atoms even existed. Neutrinos from the sun are streaming through you by the billions every second, and you will never feel a single one. Gravitational waves from merging black holes in distant galaxies are stretching and compressing the space you occupy by amounts so small that they make an atom look enormous. The universe is pouring information through you, around you, right now, in this quiet room, in this quiet moment. And the silence you hear, the beautiful, ordinary silence of a room at night, is just the universe being transparent, being clear, being readable for anyone patient enough to build the right instrument and aim it at the sky. That's why space is so quiet. Not because nothing is happening, but because everything that's happening is happening in languages that silence makes possible. The void carries the message. The emptiness is the channel. And the quiet, the lovely, deep, perfect quiet, is what lets it all come through. So rest with that. Let it settle. The universe is talking, in light, in gravity, in particles that ghost through matter like it isn't there. And the silence you hear right now is the same silence that stretches between the stars. The same silence that lets all of those messages travel, clean and clear, across billions of years and billions of light years, to reach a small blue planet where someone, right now, is lying in the dark, listening, and slowly, gently, falling asleep.